Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at nonlinear simultaneous equations. So this here, second equation, is linear. If you were to graph x plus y equals 23 in the Cartesian plane, you would have a straight line. This top equation, however, is nonlinear. If you were to graph xy equals 120, you get a hyperbola. It's not a straight line. So when we're solving these systems in which one or both equations is nonlinear, we can use similar principles to what we used for linear simultaneous equations. See, what I'm going to do to solve this system here is I'm going to look, is it easy to get x or y by itself in either equation? Well, this one is very easy. I can subtract x from both sides and make this y equals 23 minus x. Then what I'm going to do is substitute this into the top equation. The principle here is the same. We're essentially using substitution or elimination to reduce a system of two equations and two variables into one equation and one variable. So if I substitute this equation into this one, I will do just that. See, the top equation tells me that x times y, but y I'm replacing with 23 minus x, is equal to 120. So if we expand the brackets, we get 23x minus x squared is 120. So this is just a quadratic equation with one variable. We know how to solve these. We make one side equal to 0. So I'm going to add x squared and subtract 23x from both sides. And then we can solve either using factorization or the quadratic formula. So because it tends to be more popular, I will use the quadratic formula. So when using the quadratic formula, we'll first calculate the discriminant. So it's b squared, which is 529, minus 4 times a times c. So that gives us 49. So using the quadratic formula, we have x equals minus b plus or minus the square root of the discriminant. Now, of course, the square root of 49 is 7 over 2 times a, which is 2 times 1. So in there we get 15 and 8. Both of these are possible solutions. So if x equals 15, then y is just 23 minus 15, which is 8. And on the other hand, if x is 8, y is 23 minus 8, which is 15. So both of these are possible solutions. So in other words, if you were to graph this, which is a hyperbola, and this, which is a line, they would intersect at these 2 points. Let's look at another example. So let's solve this system of simultaneous equations here. We are going to do very similarly to how we did on the first slide. We can rearrange this second equation and make it y equals 3 minus x. So now that I've made one variable in terms of the other, I can substitute that into the other equation. So the first equation tells me that x squared plus y squared, so now I'm replacing y with 3 minus x, equals 225. Now I have one equation with one variable. Again, this is a quadratic that I can solve. So expanding the brackets, I get 9 minus 6x plus x squared. Now, because this is a quadratic, owing to the x squared term, we want to make one side equal 0. So x squared plus x squared is 2x squared. I've still got my negative 6x. But I need to move this 225 over here, so one side's equal to 0. So 9 subtract 225 is 216 negative. So for ease, I can divide each of these coefficients by 2. That might make it easier. Now for this one, I'll just use factorization, because it's very easy to find two numbers that multiply to negative 108 and add to negative 3. They are, of course, negative 12 and positive 9. So once again, I have two solutions for x. I have x equals positive 12 or x equals negative 9. So in both these cases, I need to find what y is. So x plus y equals 3. If x equals 12, y equals negative 9. If x equals negative 9, y equals 12. So once again, there are two solutions, 12, negative 9, and negative 9, 12. Both of these are valid solutions. And if you were to graph this, which is a circle, this, which is a line, they would intersect at these 2 points. All right, let's now look at one more example. So here we have a system of 2 equations and 2 variables. So we either want to substitute one equation into the other, or we want to eliminate one variable. In both cases, our goal is to reduce this system to one equation and one variable. So there's a couple of ways that you can do this. I think the easiest way here is if we square both sides of this top equation, I'll have an x squared in both equations. So doing just that, squaring the top equation, I get x squared y to the power of 4 equals 8100. So now I have x squared in both equations. I can eliminate x, but I can't eliminate it in the usual way. We're used to adding or subtracting the 2 equations in order to get rid of x. What I can do here is I can take this top equation and divide by the bottom equation. So I've just rewritten this equation exactly as you see it there because I'm going to divide and divide. So if I divide this expression by this, the x squareds cancel out. Now y to the power of 4 divided by y cubed gives me y. 8100 divided 2700 is 3. So I've found y, but I'm not done. I need to find x. I can substitute it into any of these equations. The very first equation up here is probably easiest. That told me that xy squared is equal to 90. Well, if y is 3, y squared is 9. So we have x times 9 equals 90. And dividing by 9, we get x equals 10. There's only one solution this time, and that is x equals 10, y equals 3. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.